This 10-line algorithm was taught as flawless for 2 decades, and almost every version of it was broken, including the one in Java's standard library, written by some of the best programmers alive. Binary search is the algorithm everyone learns first. You have a sorted list. You want to find a number. Instead of checking every element, you jump straight to the middle. Too high? Throw away the top half. Too low? Throw away the bottom half. Repeat. Every single step, you cut the problem in half. That's why it's so fast. Searching a million items takes about 20 comparisons. A billion items? Just 30. It feels like magic. And it looks trivial. 10 lines of code. A first-week concept. Surely nothing this small could hide a bug for 20 years. Here's the twist. The idea is easy. Getting the code exactly right is brutally hard. And that's not my opinion, it's the verdict of computer science itself. In 1986, Jon Bentley, the author of a legendary book called Programming Pearls, ran an experiment. He asked professional programmers to write binary search. These weren't beginners. They had time. They had a clean, precise specification. Just write a correct binary search. That's it. The result? 90% of them got it wrong. 9 out of 10 professionals could not correctly implement the algorithm they'd known since school. The off-by-one errors. The infinite loops. The boundaries that didn't quite line up. The simplest algorithm in the book was a minefield. So Bentley did the responsible thing. He wrote a version, reasoned about it carefully, and effectively proved it correct. This was the gold standard. This was the one you trusted. And for the next 2 decades, that proven version spread everywhere. Textbooks. Courses. Standard libraries. It was treated as untouchable. Case closed. Except it wasn't closed. Because a proof is only as good as its assumptions. And Bentley's proof made one quiet assumption that the real world would eventually break. Fast forward to 2006. Josh Bloch, one of the architects of the Java platform, is looking at the binary search inside Java's own standard library. The same trusted implementation. And he spots something. One line. The line that finds the middle of the range. It reads, mid equals low plus high, divided by 2. Mathematically, that's perfect. The midpoint of low and high really is their sum divided by 2. Any math teacher would sign off on it instantly. But computers don't do pure math. They store numbers in fixed-size boxes. In Java, an integer maxes out at about 2.1 billion. Go one over, and it doesn't get bigger. It wraps around. It flips negative. This is integer overflow, and it's silent. No crash, no alarm. The number just quietly becomes wrong. Now watch the trap. If low and high are both large, say around 1.5 billion each, their sum blows past 2 billion before you ever divide by 2. The sum overflows, becomes a negative number, and mid turns negative. Then the code tries to look up a negative array index, and everything explodes. For arrays small enough, this never happens. And in 1986, no computer could hold an array that big anyway. Bentley's assumption was true, for his era. But hardware kept growing. Memory ballooned. Eventually arrays with over 1 billion elements became ordinary. And the bug that was theoretically impossible became very, very real. So the proof wasn't wrong. It was correct, inside a world that no longer existed. The assumptions rotted while the code stayed the same. And the fix is almost insultingly simple. Instead of low plus high over 2, you write low plus the quantity high minus low, divided by 2. Same answer, mathematically. But now you never add the 2 big numbers together. The subtraction stays small, the sum never overflows, and the bug vanishes. Bloch titled his write-up with a confession: nearly all binary searches and merge sorts are broken. Not the textbook's fault entirely, the world had simply moved. So what's the real lesson here, beyond one clever line of code? It's this: correct is not a permanent state. Code doesn't rust, but its assumptions do. Every program you write rests on invisible promises. That numbers won't get too big. That inputs stay in range. That the environment behaves like it did on the day you tested it. And a mathematical proof only guards the logic. It says nothing about the machine underneath, the finite memory, the fixed-width integers, the messy physical reality. That's why the best engineers stay humble about simple code. The scariest bugs aren't in the 1,000-line monsters. They're in the 10 lines everyone assumed were perfect. Binary search wasn't broken because programmers were careless. It was broken because being right today is no guarantee of being right tomorrow. And that quiet truth outlives any algorithm.